Welcome back to our channel, great people. Today we'll be continuing our image classification, detection and segmentation series. So far we've carried out image classification with both PyTorch and Tensorflow. If you've not seen that, it is a very interesting tutorial. I will advise you to check it out here. We did an incredibly exciting project on skin disease classification. Very interesting one. Just check it out here. Today, however, we will be moving to another very important part of computer vision, which is object detection. Now, computer vision has three major areas. One is object classification. Here we'll ask the question of, is this a cat or a dog? Another is object detection. Where is the cat in this picture? Can you draw bounding boxes around it? And then the one for the senior boys, segmentation. What pixel interprets our object in this image? Can you trace it? We treated classification in the previous projects, as you all know. We now want to look at detection. How do we intend to do that? There are very many ways we can carry out object detection, but we will be interested in the most basic approach. Please, not the best, but the very basic approach, and that is CNN. Yes, the same CNN that we used earlier and throughout this series. But first, let's do a short recap of convolutional neural network, CNN. What did we say CNN is? A convolutional neural network is a class of deep neural networks most commonly applied to analyzing visual imageries. CNN is an improved version of multilayer perceptron. It's a class of deep neural networks inspired by human visual cortex. Basically, CNN works by collecting matrix of features, then predicting whether the image contains a class or another class based on these features using softmax probabilities. A convolutional neural network is designed to automatically learn visual patterns from images. It does this through convolutional layers that detect edges, features, and shapes, pooling layers which reduce spatial dimensions while keeping essential information, and finally, fully connected layers that perform the final classification or regression, as the case may be. For image classification, the CNN simply outputs which class the whole image belongs to. For example, there is a cat in this image. But object detection is a bit different. It asks a deeper question. What objects are in this image and where are they located? That is what makes the problem special. The model must locate objects by predicting bounding box coordinates along with class probabilities. How will it do that? Now, the basic CNN has the convolutional layer for feature learning, as we know, and I've explained in the previous videos. It now has to add two extra outputs to its design. One is the classification head, and the localization head, or as most commonly called, the regression head. It is a classification head that will answer the question of what exactly is in this picture. Is it a cat? Is it a dog? Or, in fact, nothing of interest. It produces discrete categories. However, the regression box provides continuous outputs, which tells us where the coordinate of the object of interest is in the image. Is that not simple? Yes, it is very simple. It is that simple. This is in fact a simplified architectural illustration of CNN for object detection. The outputs are trained jointly using one network and optimized through joint loss functions. Now let's get more practical. Today, as always, we'll be using this approach to solve a big societal problem. We'll be detecting tumors in brain images um, from from medical images, medical scans images. So let's get cracking. Um, as with our previous two projects, I will be using the Go Collab, um, simply because it has the resources that you actually need for our project. Resources that will be we may not have locally, even though it's not such a demanding project, but it can be sometimes. So it's just right to just use collab, since everybody that can want to use this has access to a Google, should have access to a Google account. Remember that this is a code along series, so everything here is done from scratch. So this is the process we'll follow. This is the methodological steps we'll follow in design this project. First, we'll import the library, then we'll load our data set, our brain MRI scans, then we'll carry out pre-processing on the data sets as usual. Then we'll design our CNN model. Then of course we'll carry out the training itself. We'll test our model on the validation data set, and then we'll try to see how our model can be used to make prediction on a new image, basically a new unseen image. So as I said, our data itself will be um, brain scans. It's an open source data set. Of brain MRI open source data set. We can easily get it from Kaggle. We can get it from RoboFlow. Can get it from several GitHub pages. It's basically for research, so it's free. And then but I'll also drop a link to my Google Drive, of course, as usual. I'll drop a link to the data here. But let me just walk you through the data. So this is it. This is the brain cancer detection data set. Um, so let me just open one of these. So you have there are two things we are interested in: the image and the annotation files. The annotation files will give you a location of the boundary boxes. So let me just open one of these annotation files. Um, we This is the height and width of the image. This is the ID of the image, the date of capture, and this is the file name. But I'll not really be interested in that. I think we should just go down, because these are for all the images, so it's maybe a lot. Okay, this is what I'll really be interested in: the annotations. Yeah, the annotations has the ID, the image, the category, and the bounding box. Right, where did we get the ID from? The image ID from. The image ID, we could have gotten it from here. We have the here we have categories, right? We also have sorry, we also have images, because this is a JSON file. We have licenses, we have info, we have categories. I know we have images. Yeah, this is it, the images. And the images is where we'll be able to retrieve the address, right, and the size of the image, the height and the width. Then from the annotations which we have down here, we'll be able to retrieve the bounding box here, the bounding box which is this. It's just there's a segmentation, it's just bounding box, and that's that. So you see how we retrieve that. So let's go back to our code. So the first thing we do is to import our library, right? So we import JSON. JSON will be used to figure out the annotation files. Always, of course, for the path, and a random because you may need to check some images randomly. The numpy, of course, for numerical data manipulation. Pandas for data frame. Tensorflow for our model building, and in fact, the project as a whole, um, Keras, and all this for model building. We have scaling for splitting our data set into test chain. Validation, we have matplotlib for plotting making our plots, either plotting our image or um, making our plots after we've actually done our prediction. Then CV2 is used for manipulating images in Python. All right, so this library should not be strange if you've been following our series. Then we go to our next step, which is loading our data sets. So first of all, we are going to get the address to the data sets. I have my address here on my Google Drive. I'm going to use the one that's inside the train. Remember, you can join all of them and use to give you better results. I just decided to use the train so that it will be faster to carry out our training. Then, of course, the image size. Why I put this here is so that I will not just do it again. Whatever the image size, I'm assuming that we may have different image sizes. So I'm going to standardize everything to 224 by 224. Okay. So then the next thing is our annotations. So we've already given the address to the annotations. So what we will now do will be we will now manipulate the annotations to get the different files that we need. So what does this block of code do? So this block of code loads the brain cancer data sets annotation from the .json file that we have here. Um, this is the this is the cell we are now. So it loads this one. Um, then he extracts the links of each image file to his bounding box coordinate and the label. Of course, it's just the one label. Then it normalizes the bounding box so that they will be scale invariant, and then produces three clean lists which will be used for training. Here, right? So it gets normalizes here, but let me just show you how it does that. So first of all, like if you remember what I showed you when I just hope the annotation is still open here. Oh no, I think I'm right. Oh, no. All right, so we have this as I remember I said that we are interested in the images because the images contains the address um and the height and the width, the images dictionary, right? um the images section of the JSON file, right? The images key of the JSON file. So we have it here, right? That this is the images, which it is from these images that we'll get the. If you look at this, one of them is annotation, which we are going to get the bounding box, and the images where we get the location, the address. Beautiful. So we need a path, which will create an empty list. Then the labels, which we just be adding the labels, whatever is one label, we'll just be adding it to it, just for the the classification head just to do its thing. Remember that we can use this algorithm if we have more than um, one class in our image. So let's just generalize, even though it's just one class we have. Then of course the bounding box too. Just create an empty list. We'll put the different bounding boxes. Remember, the bounding box will have the height, the width, right, and the center. With that, you can know the difference, the way the bounding box is. So we'll just map the label to the ID, which will just be a one-to-one mapping, and then ID to a label. Also, well, this is just the inverse of this, right? For example, 0 will mean nothing, then 1 will mean it has seen a that it has seen a tumor, right? So that its tumor will just be what will just be there to just be one class, one label to one ID for this project. Beautiful. So we'll start with the first ID, which is 0. Why am I starting with 0? If you look at this, I hope I see, yes, you can see the different IDs. We have 0, the next one will be 1, and the next one will be 2. So we start with 0. That's why we're saying next is 0. Okay, beautiful. So items 2 in zip, data 1, data 2. So what this does is that it gets the path, right? Here. So you get the item. When you go to the item, which is images, all right. Yeah, images, right? So it gets everything here, everything within here. Just take this inside, don't close it. Everything, it gets everything within here. It gets everything within here. What am I interested in? I'm interested in you can see the file name, right? So um, the file name key of this dictionary, the file name key of this dictionary. Okay, so it gives the file name. We're interested in the file name, and then um, which will be the path. Put in the path, then we'll now join it. Remember, we are just joining this to the general path. That's to the train folder where our images are located. So you then append the files to this, the path to this um, list that we put here. Then of course the labels will just be the categories and um, just the categories. So it's not really fun because it's just one category. So that's not really important. Then the item width, um, you can see this is, remember, this is still our item, which is this one. We need the width. You can see the width, which should be 416, and the height, which is 416. It may not be 416 throughout the whole image, so that's why um we just need to add it, because we know it may not be 416 for the entire image. It's large image, so I did not go through everything, but I know it cannot be the same. So we have this as item width, item height, which will be our width and the height. So our bounding box, that is the x, y, w, and this. So where do we get it? We use item 2, which is the annotations. Item 2, which is the annotations. So let's go down. This is still images. Annotation starts here. Annotations will start somewhere here. You can see it here. These are annotations. And when you open annotation, we have ID, image ID, category, which is 1, and then bounding box, right? These are the different positions of the bounding box, right? Okay, so we have 4, and then we now put them here, right? We then put them here, uh here. Okay, then we now normalize. This is the normalization where we divide everything by the width, so it will be between 0 and 1, and this goes to here, and this goes with these two. So it's just that simple. Then of course we change this to numpy array because of what we need for we need it for numpy array. So that when we are doing our training, and then we convert this to numpy array too, and we get the number of classes, which of course will just be the length of the label.id. In this case is 1. So we just run this. So that's for, I don't think I run the one on top. Yeah. And then now run this. So that's for that stage. What is it? JSON is not defined. Did I run this cell? No, I did not. So then just run this. And then beautiful. And then let me run this again. Right, so everything now works. All right, so the next stage should be for us to carry out pre-processing on our data sets. So this stage, the pre-processing our data set. So we'll have a function here first. This function will define how each image should be read and transformed. Um, yeah. So we know that the TensorFlow, we have the TensorFlow tf.data API, which we call this function for every sample, right? And it takes the image file path, the label, and the bounding box. So the first thing we do is to read our image. This reads the image directly from the disk into a TensorFlow byte string, right? The variable path becomes comes from our earlier list of image paths, and then of course this is what we call lazy loading. It does not load all the images at once. It loads them. What this does is it loads the images in batches, right? This is so that it allows training memory efficient even for large data sets, because only one batch is loaded at a particular time. All right. So for the next this next line, image.decode JPEG does is that it converts the raw byte string into a numerical tensor, right? What we have, this channel is equal to 3, ensures that it always outputs an RGB. We have 3 channels RGB, even if the original file is grayscale, but of course we have to generalize because it's not every time that we have um we don't expect, probably if technology gets better we may have colored images. uh they see, of course, why is this done? That's because the CNN expects numerical pixel data, not raw files, right? So this line itself transforms our image from our image files to an array of pixel values. So the next one here simply resizes our image in order to be consistent. We have consistent dimensions. Remember, we set it earlier to 224, so to make it 224 by 224. This ensures that all input tensors have the same shape, which is required for batching and for the CNN input layer. Have the TF casts this here, right? So what this does is that it converts pixel values from integers, which is 0 to 255. Of course, our colors RGB is always from 0 to 255. So it brings them, it normalizes them to floating points of between 0 and 1. That's why you are seeing it divided by 255, so that for normalization. Then that's because neural network works best for small consistent input ranges rather than large input ranges. Of course, this is what you are going to return, the basically the most important line, right? It returns the image first. Um, that is the process image tensor, or rather, or you can by extension say the model. The model also, it also returns a dictionary with two keys. One of them is a class input, a class output, right? That's this. No, the first one is the image, then returns this. One of the this is a class output, right, which will be a one hot encoder vector representing the tumor class label, right, which in our case will just be one. And then we also have the bounding box output, which is the corresponding bounding box coordinates. That is the x center, the y center, the width, and the height. Of course, with that, we can always know because if we have the x center, the top the top will be the width divided by 2, right? Um, yeah, yeah. And then while the other one is divided by 2, with just the center and the center and the height, we can get the different coordinate. Remember, we have where the center is, and we have the width here, which we need to cut the center through the middle, and we also have the height, which will cut the y through the middle. So that's what it returns at this point. Why is this really important? The CNN has two outputs, namely class output and VBox output. Remember, I said that we have two heads, the regression head and the classification head. The regression head is also the localization head. Now, TensorFlow matches the dataset dictionary keys with three-layer names automatically during training. This itself is what allows you to train a multi output models in one unified pipeline. The next cell here creates a TensorFlow constants, which we'll use throughout here. So the path, um, we have the path, we have the labels and the TensorFlow boxes this here, right? We have it here now. What this does is converts Python lists, which was provided from here, right, into TensorFlow tensors. Remember, we got them from into TensorFlow tensors, so that they can be fed into TensorFlow data sets, which is here, like this, which is here, right? That's because remember that we return list here, and TensorFlow, we have we have our Python image part here, which was a list. Can you remember we opened the list? The labels was a list, we opened it, and big box was a list, we opened it, or rather a non-pi array to say. We have to change it to tensors. Tensors, not enough. We have to change them to tensors from those non-pi arrays, right? The TensorFlow tensors. Um, okay, so TensorFlow pipeline, of course, works with tensors, not a conventional Python list. Then the next thing we have here is TensorFlow.data.dataset. What this does is that it creates a data set where each record is one tuple, right? This data set can now be mapped, right, bashed and shuffled efficiently on your GPU or your TPU, as the case may be. Have the dataset.map, right? What the dataset.map does is that it applies the load and preprocess, which we had already written here. It applies this load and preprocess function to each element in the dataset, right? The non-parallel is equal to this. What is equal to this? What this does is that it tells TensorFlow to automatically use multiple CPU threads for faster loading and pre-processing. Why do we really need these two lines? Why do we need to do this, right? That's because all these two with the two things inside here is because we need the data pipeline to be asynchronous, right? While the GPU trains in one batch, right, the CPU should be preparing the next one in parallel. That's
what this allows you to do. That's why you're seeing number of parallel calls, right? Okay, beautiful. So this is this is just telling you how your training data set is going to take, and how it's going to take 16 images in a batch. Correct. The batch will be 16, and then it will be this is the shuffling, the shuffle and the random key, and then yeah, this also tells you how the validation data sets will be selected. So that's basically what this does. This is just conventional, but these are the major things which I hope you understand. The meaning of each of these lines. Please, if you don't, just write in the comment box. All right, the next step will be the model architecture, which as usual is the most important part of our algorithm. As had explained, to be a multi-task CNN model with one shared backbone for feature extraction and two output heads, the classification head and the regression head. So now let's go on to explain what each line in this architectural design, what each line means. Right, we have this as the function head, right, which takes they put the input shape and the number of classes. So first of all, it gives the size of the image, which should be 224 by 224, and then this is 1, right? Then we have the number of classes, which in this case will also be 1. So what it's this input shape gives the size of each image, right? It tells the TensorFlow the shape of data that will enter the model, right? Okay, beautiful. Now for this, what does this do? This creates a keras tensor that serves as the model's input node, the model's input node. Every layer will connect to this original tensor. In mathematical terms, it's more like x naught, more like the x naught, the initial, right, which is the input vector representing image pixels. Then after that, we have this look at these three lines, right? So let's break down those three lines. The first one there, which is a conv 2D 3233 padding same, right? It applies 32 filters, that is 3 by 3 kernels. 32 filter 3 by 3 kernels to extract local special features. For example, the edges, the texture, and the intensity gradients. Each filter slides over the image and computes a dot product. Or rather, or you can say a feature map. Now, what does the second one, the leaky relu, do? What does it do? The leaky relu 0.1 applies a non-linear activation. Unlike the conventional relu, which zeroes out negatives, the leaky relu allows a small slope of 0.1. That's why we have here, right? 0.1 for negative inputs, preventing neurons from dying over time or decaying over time. Then we have the max pooling 2D. And max pooling 2D, what this happens is that it downsamples the feature maps by a factor of 2. That's, in other words, it takes a map of 2 by 2 region, it picks a 2 by 2 box, and then down samples everything, it's more like it reduces the the area of what our model is going to look at, right? As it reduces the spatial resolution, but keeps the most important activations, making the model translation invariant and even more memory efficient. With that, we now move to the second convolution box, right? The second convolution box. So it's basically the same thing as what happened, very similar to what happened earlier, right? What happens is this. The first here, of course, doubles the number of filters. Before it was earlier, it was 32. Now it is 64. This is so that you can learn more complex features like edges, corners, textures. After the first block has captured basic local features, this one is expected to start combining them into mid-level patterns. All right, so just basically the same thing as the first one, but just at a deeper level. Then of course we now go into the third convolution block. So what this does is that it expands again to 128. First one was 32, then 64, then 128 filters for richer and high level features. After 3 rounds of pooling, the spatial dimension is reduced, right? From of course, earlier it was 224, but if you've seen by the um um the max pooling that we've done, it has deteriorated to 28, right? Leaving the more compact feature maps that is expected to summarize the tumor region, the brain tumor region. This backbone is what actually does feature extraction. You should note that up to this point, every layer is still spatial. It still has the height, it still has the width, and it still has the depth. Then we now have the layer where we have the flattening, the dense, and the leaky relu and the dropout. I'm going to explain this now. What this layer does. What we call the flattening and the dense layers. Right after this layer, after these 3 layers, we now come here that flattens it. What the flatten does is that it turns the 3D feature maps into 1D features, or what we call feature representations. Dense, on the other hand, um what dense is that dense 256, what it does is that fully connected layers with 256 neurons learns a joint representation from all the extraction features, right? It creates two fully connected layers with 256 neurons, allow it to learn joint representation from all extracted features. Then, of course, the leaky relu introducing non-linearity, again, the same way that done, right? Then, dropout of 0.5. What this means is that it randomly drops 50% of neurons during training. This is more like a regularization technique that prevents overfitting, right? Especially when we are dealing with small medical data sets. Of course, getting very large medical data sets is actually not very cheap. All right, so we've looked at dropout before in the previous video, so you can look at it. But what it does is just like poke holes in the data set that our our model is expected to double guess. So after this stage, you should have a compact high level vector which can now describe what and where the tumor, your particular tumor might be. All right. So now we now have the dual output heads at this point. Remember, I said we have two heads: the regression and classification head, right? So we have the class output, which in should be our um the should be our classification head. What it does is that it uses a softmax, right? It uses the softmax to output probabilities, um, which in this case should sum up to 1, right? The one with the highest will be taken as the class of what it has seen should be. What it has seen should be. Then you now have the B box output, right, which is the regression head. It predicts the boundary box coordinates, which will be your x center, your y center, your width and the height, normalized between 0 and 1, right? Number issues. This is what makes it to be normalized between 0 and 1. Of course, sigmoid is always more like tan thing between 0 and 1. Then this is your model definition, which builds a multi output keras model that maps the input image to class probability and bounding box coordinates from this. You can see it maps the input to what you got here. So that is what this does. And of course, it then this is the model that is finally returned. Great. After this model has been, this architecture have been built, we will want to compile it, right? This is just creating that model. We want to compile it. So this itself runs this. This itself runs this function that we designed. Just finish design the model itself. All right. So the next thing is for us to compile, right? In the compile, if you look at the compile, we have um 4 lines. We have the optimizer, we have the loss, and we have the loss weights, and we have the matrix. So what happens here? The optimizer, this one, what the optimizer does is that it uses the Adam optimizer, right, to carry out adaptive learning, because each of the neurons has weights, right? Which neurons is more important? So it helps in the learning process, right? And this is basically your learning rate. How well does it learn, and how should we tweak each of the weights? Like, okay, this, you should prioritize this feature over the other feature. Then what loss are we going to use? Um, Here we have two losses. The classification, which we use categorical entropy, because you know that cross entropy is one of the most popular um, losses for classification. Of course, you know what losses does. It is the loss that will give you that will tell you the error, right? And then it will inform the way you are going to tweak it. And then for the bounding box, we are going to use the MAC error because it's a regression problem. Then we have the loss weight, right? So what the loss rate is, the bounding box is weighted 5 times stronger than the class loss to make sure that localization is not in null, because it is easier to get the class correct than to get the bounding box correct, because bounding box is a regression problem. You have an infinite number, infinite, it is continuous and infinite, but this class output can just be very small. All right, so this just makes this far more prioritized than this, right? Okay, beautiful. Then the matrix for the entire model will be the class output, which will have the accuracy. You know what accuracy does in classification. It tells you the the true labels and the false, what it has seen, what it has predicted as true all over, what is actually true on ground, and what that's predicted as false, and what is actually false on ground. So it's more like uh, the accuracy. So the formula is here. If you don't know the formula for accuracy, then the bounding box output, we are going to use the MSC. So those are just the metrics. So what this summary does here is that it gives you a summary, right? A detailed architecture summary, including the layer names, output shapes, the number of parameter layers, and the total chainable parameters. That's what the summary will give you. So let's just quickly run that and see what we have. Oh, let me just check that we are run this preprocessing. No, we did not run it, which is strange, right? And then this, which is explain now. I hope, yeah. And this is our summary. This is our summary. You can see everything here: the layer names, the output shapes, the number of parameters per layer, and the number of trainable parameters. All right. Great. So now we carry out the training process itself. Um, So what this does is just modeled of fits, just the way we in our sklearn, and then we give you the training data set, the validation data set, and the number of epochs. All right, so I think we'll wait while it trains. So therefore 30 25 images. So we just wait while it will train, just 10 batches. So I'll just leave it here, then I'll come back when it is finished training. Oh, all right. So I think it's finished training. Um, yeah. So we have each of the epochs here up to the 10th epoch, and this is the bounding box output loss, the class output accuracy, which had been explained earlier, validation output loss, and validation output MAE. I've explained that to be accuracy, the way that will be used. Yeah. So that's it. That being done, we want to test how well our model um, performed on the validation data sets. So, um, yeah. So, we need to. mm, So, we need to test on our validation data sets. So, we need to test on our validation data set. So, how do we do that? Yeah, we've already done model training, and then all right. So, I'm going to explain every single line of this code. So, generally, this function takes one batch of validation data, right? Then gets the model prediction, both the class and the bounding box, and then visualizing them on top of each image so that you can inspect whether the model has learned to localize or classify locally. So, of course, this what this does is that the it's the values, right? It takes the values is your TensorFlow validation data set, right? So this one means that it retrieves one batch only. Remember, the training is done batch by batch. Um, the for loops unpacks the tuple returned by the data set, right? Remember that the batch size was 16. If you remember from our training data, we had a batch size of 16, which had been set earlier. Trying to find it. All right, so we can see here, this was our batch size, which was set at 16. Yeah, and okay. So the right, so the for loops unpacks the tuples which have been returned by the data set. The image batch, of course, is a tensor of shape and batch size, image size and 3, which signifies the input images. Then the target will be a dictionary containing the class output and the bounding box output. So the purpose generally, as I said, is to load one mini batch from the validation set to inspect predictions virtually. So what this does is it passes the batch of images through the trained CNN. So since the model has two outputs, the prediction results predict is a list of two arrays, which is the predict, the pred 0, which is the predicted class probability for each image, um, um, and the predict 1, of course, the predict bounding box coordinates for each image. One of them is the probabilities, while the other one is the bounding box coordinates. So generally, the purpose of this to say is to get the tumor classifications and prediction boundaries from for the batch. All right. So the next one is this. What does this do? The purpose of this is to convert probability distributions into district tumor classes. Then the B box prediction. This of course prepare to denormalize and plot each predicted box on its corresponding image. This here contains the bounding box prediction for each image in the batch. Of course, each element contains the x center, the y center, the width and the height, all normalized between 0 and 1. Then we have the nested loop here. You have the nested loop there, which um, will help us visualize the prediction one image at a time. It iterates through all the image in the mini batch, right? Or that is for the 16 images, and then it will visualize the prediction. It will just to help us visualize the prediction once at a time. So this um converts the TensorFlow tensor for the ith batch image to a NumPy array. Um, this allows us to use standard plotting libraries, allowing us to use standard plotting libraries, right? So that itself retrieves the model's predicted bounding box for the image. This right? It's retrieves the model's predicted bounding box for the image. So this, as you can see, converts the CNN predicted coordinate into the same scale as the displayed image. How does this do? How does it do it? The XC that you are seeing here um minus um how does it do it? It does it by normalizing the predicted bounding box so that it can be drawn correctly over the image. And remember that the XC minus BW over 2, right here, moves from center to the left edge. This moves from the center to the top edge. So multiplying image size converts normalized coordinates back into a pixel units. Remember that it was between 0 and 1. So you multiply by the size, it will take us back to the original size. It's more like undoing what we had done earlier. And then what this does is now is that it now creates a subplot, matplotlib subplot, and make us prepare for our plotting. So what this does on its own is that it helps us draw a predicted bounding box right on the image. Remember, it has given us prediction, so we draw bounding box on the image. Um, so the yes, so the patch, the rectangle is more like a tool for drawing rectangles. If you remember, we had already imported this at the beginning. So let me take you back. Right. So for matplotlib for patches, so we are using the patches to draw that on the images. Then of course we add the patch, right, which overlaps the rectangle on the image, and then we set our title. So that is that for here. So this just basically takes a prediction, right, makes the modeling base per batch, right. This is one image at a time. Takes the prediction per batch, right, and then gets the class prediction and the box prediction, and then carries out the plotting here. Beautiful. So let's just run this and see if we'll get anything tangible. Did I run the last one? Let me see. Yes, I think I did, which was the training itself. If I run this, let's see how well our model will predict. Okay. Uh, these are all the validation images, and you can see it has picked the cancer or the tumor in this case. Remember, this is not that to give because it was only 5 epochs that I trained, so it won't really give you the very best of results. But you can see it's very close to this. So if you want to have perfect results, I will advise you to train on more epochs. All right, at least for most of them, it sees the cancer images. All right. So what if I want to use this model to make predictions? To carry out predictions itself. So we have a predict on new image function here, which helps us do that. So what this function does is that it takes a file path to a new image, right, and then processes the same way it did during training, runs it through the trained CNN, and then visualizes the class and predicted boundary boxes on top of the image. So let's start from the beginning. So what this does, it sets up the interface for making our prediction where our model will be our trained CNN, our image parts will be the part to the image we want to make prediction for. The class label will be the class to index that we have created earlier. Let me just show you if you've forgotten. Remember we did it here, which I said is not extremely important. It should be here. Yeah, it's here. All right. ID to label and label to ID. Then our yeah that's our class labels, and then um the image size will tell you the image size dimension. In this case, you choose 224 because of what we used. So cv.image, what this does is that it reads the image parts, right, and reads the image from the image parts. Then what this does is that, so if there's no image, it's going to return image not found here, right? So what this does is that it converts to from BGR to RGB. Why so? Because CV2, what CV2 does, remember when we did an open CVs, what CV2 does is that CV2 reads image as BGR for whatever reason. So if you plot this, it's going to blue will be see itself as red, while red will see itself as blue. Okay, so it will look like an inverted image. So you have to return it back to its normal way it should be. Then the image resized is you resize. We are going to resize CV2 that resize. What this does is that it resizes our image into 224 by 224, so it can fit with what we used in training. And then of course, what this does is it normalizes. You can remember, just divide by 255 for the normalization procedure. All right. So then what this does is now it gives them it does the prediction itself, passes the model to your CNN, right? And then gets the class prediction and the bounding box. Remember, we have two class prediction and the bounding box. Then um, this converts a probability distribution into a discrete class ID. How so? It's going to give you probabilities of this being a particular class. We just have one class, but if you had more than one class, it will give you probability for each of those class. So this arc marks now will give you the one with the highest probability. and then it will now map it. You can now use this to now map it to now map it and have the class that is it is synonymous. Remember that it will give you the index of the one with the highest probability, and then based on that mapping you are done, you know what class that is. So the BB box, of course, is what it will give you here. You can print this out to it to give you here. Then um, the next thing is for us to normalize our coordinates. Remember that our coordinate was normalized to 0 and 1. So to bring it back to how it was, we have to multiply by the image size. That is just what we are doing here. That's what you are doing here to take it back. Remember, it was 0 and 1. You have to bring it back to the size I told before. And then we do the conventional visualization that we did for our validation. We do the same visualization here, the same steps. So it's not anything new. And then let's just run this. So I got an image, and you can try with other images. So this is the address to that image. Then I now run this function, implement this function that I had created here. All right, so you can see it can detect our tumor here, and at this location, which is quite impressive, very impressive for an image that I had not seen before. All right, so that is that for this. It's been a pretty because of how detailed it is. It's been a pretty long tutorial. So so that is that. So um, what we do is we try to implement the same code with PyTorch. Try to implement this same algorithm with PyTorch for our next video. But in any case, if you have any question, don't fail to drop it and also send it to the email. So I'm going to send the link to this code, which you find it in my GitHub, and also we'll see you in the next one. Thank you very much.